Okay, so we're going to talk about intermolecular forces and how in the world these things have effects on the way the big groups of molecules sort of interact together and how they behave together. So first of all, we need to define what in the world are intermolecular forces. Well, these are the forces of what keep molecules together. So we're not talking about like what's happening within a molecule. We're not talking about a bond between a carbon and an oxygen. We're talking about one molecule that has carbons, oxygens, hydrogen, whatever it may have in it, interacting with another molecule that has carbons, hydrogens, oxygens, whatever it may have in it. So consider this like how your left hand is going to interact with your right hand. That would be one way to look at it. If you have a stronger intermolecular force, in other words, you have a force between molecules, that's what this term means, intermolecular, between molecules, you have something that sticks them together. Well, if you have something that's stronger, that's sticking them together, that means that they want to stay together. Why does this matter? Well, it means that molecules that want to stay together want to be a solid together. They want to be a liquid together. They don't want to be a gas and be further away from each other. On the other hand, if you have something with a weaker intermolecular force, the molecules are not really bound together as well. So I kind of see this as how much stickiness we have between the molecules and how much they want to stick together. So the difference might be a set of balls with like Velcro attached around them versus just a set of like ping pong balls with no Velcro. Ping pong balls with no Velcro are going to like fly apart really, really quickly versus those that are stuck together by that Velcro maybe don't want to fly apart very easily. This ends up affecting solubility, melting points, and boiling points. And that's why it is incredibly important to understand. Okay, so let's talk about the strength of our intermolecular forces. The weakest are things like nonpolar interactions or London forces, London dispersion forces. Sometimes you hear this even referred to as LDF, and that stands for London dispersion force. The next is a dipole-dipole force. Sorry about that. I should not use that. I should use this. So a dipole-dipole force. Next, we have stronger bonds, which is a hydrogen bond. Now keep in mind, hydrogen bonds say that they're a bond, but it's still an intermolecular force. It's not an actual bond between two molecules. And then finally, we have ionic bonds. So I want you to remember that when it comes to things like ionic bonds, this is an actual positive charge something with an actual negative charge something. These two, dipoles, and hydrogen bonding, we talk about partial positive and partial negative charges. So it's like you have a little bit of positive and negative, or mini magnets that are sticking things together. And London dispersion forces, they kind of just lay on top of each other, and that's really about it. We can justify it and say other things about these types of interactions, but in truth, they're kind of just not so much there. So let's review things based on this chart. First of all, keep in mind when we're talking about all of these guys, we're talking about when you have lots and lots of molecules. So nonpolar interactions or London dispersion forces, things like just carbon and hydrogen compounds. So like C2H6. This guy's melting point is negative 183 Celsius. In other words, he ceases to be a solid and is now a liquid, way low temperatures. And the boiling point is negative 89 degrees Celsius, which means that at room temperature, this guy is going to be a gas. Next, we have dipole-dipole interactions. Sorry, I didn't color coordinate with the top here, so let's try to do that. Dipole-dipole interactions. Well, this type of molecule that you see right here has a dipole in that we have this partial positive area and this partial negative area. What causes that to happen is that oxygen is more electronegative and it starts to pull electrons towards him. And so you get a partial negative charge at oxygen and a partial positive charge around carbon. So let's look at how this affects the boiling point and melting point. The melting point here is negative 92. Now note that that is higher than what we just talked about. And the boiling point is negative 19, also higher than what we just talked about. I'm keeping them about the same size, so this is not a size difference. Next, we have hydrogen bonding. Now, hydrogen bonding is really just a dipole-dipole bond, but it's a special kind of dipole-dipole bond. So if we talk about methanol, so CH3OH, this guy also has a partial negative charge at oxygen and a partial positive charge at both hydrogen and carbon. I'll let you all build that one. Now, this melting point is kind of on the same order as what we just saw with the dipole-dipole interaction. But wow, what a difference the boiling point is here. Because this guy is now 65 degrees Celsius, which means that at room temperature, methanol is actually a liquid. Okay? So that makes a huge difference. Sorry, I'm going to move on up here for discussion of ionic bonds. Well, ionic bonds are actual positive and actual negative charges. So if we look at NaCl, that would be Na plus and Cl minus. Huge difference here on both melting and boiling points. Think about this. NaCl is table salt. That guy has a melting point of like 801 degrees Celsius. In other words, he's a solid at room temperature. The boiling point is over 1400 degrees Celsius. We're talking about way high temperatures. So yeah, these interactions make a huge difference as to what boiling points and melting points look like, and also how these molecules behave, maybe at room temperature, maybe at body temperature. So it would help us to sort of identify what functional groups have each of these types of intermolecular force really at play. So let's start then with nonpolar interactions, or London dispersion forces here. These tend to be molecules with just C's and H's in them. They can, like these structures that you see here. So in other words, they're big, long carbon chains or short carbon chains, whichever it may be. Typical types of compounds that contain these things: oils, fats, and lipids. That's sort of what we're going to talk about as we move on. The functional groups would include alkanes, alkenes, alkynes, and then the cycloversion of cycloalkanes and cycloalkenes. Sorry, I put cycloalkynes, but really what I meant is cycloalkenes. Cycloalkynes are pretty rare. Okay. Next, we have dipole-dipole interactions. So these are molecules with partial charges. As we were talking about, you've got the electrons from this bond that's being pulled upwards. So the electrons are pulled towards oxygen. But we don't have oxygen directly bound to hydrogen. That is a specific hydrogen bond. So we'll talk about that in just a second. So functional groups that we're talking about here: ketones, aldehydes. We also have things like thiols, ethers, esters, and then some stuff with amines. So I'm going to talk about amines here in just a minute. But tertiary amines would be included here, and tertiary amides. Okay, next we have hydrogen bonding. Hydrogen bonding is incredibly important. Hydrogen bonding is still a form of a dipole-dipole bond, but as I said, it's a special form of it. So what makes a hydrogen bond is that nitrogen, oxygen, or fluorine is directly attached to hydrogen. And so what this does is it means that oxygen, nitrogen, or fluorine are incredibly electronegative. They pull electrons towards it. And that leaves hydrogen much more positively charged. In other words, it's more than just a partial positive. It's like a partial positive positive. And oxygen would be like a partial negative negative. And that's what makes sort of such a closer to a larger differential in charge in this case than you have just in a regular dipole-dipole bond. So I drew for you sort of what that looks like with some water molecules here. Note that when we're drawing these intermolecular bonds, I'm representing that by dashed lines between oxygen and hydrogen. I kind of consider this like if you've seen like athletes come into a crowd and they sort of like shake one hand and they go to the next hand and they shake it and they're still holding on to the first one, and then they pull away from the first person and they hit the next person's hand, and that, you know how they keep on climbing through people's hands. That's how molecules are interacting. And hydrogen bonding, that's sort of what's represented by those dots that are there. So what are we talking about here? We're talking about, oh, sorry, I didn't mean that to have that too blown up. Alcohols, carboxylic acids, primary and secondary amines, and amides. It means primary and secondary amides. Okay. Finally, let's talk about what ionic bonding means. Well, ionic bonding happens most common in the field of organic chemistry when we have an acid-base reaction that's taken place. So we're not going to see that totally until, a day or two from now. But what can happen is that something that's an acid, like a carboxylic acid, can end up losing its hydrogen. And when he does that, he gets a negative charge. See how there's that negative charge that I just highlighted there? Or you can have an amine or an amide that takes on an extra hydrogen, and that results in a positive charge. So this is pretty rare within the field of organic chemistry. Well, no, I wouldn't say it's rare. I shouldn't say that it's rare. It's more that you're not going to see it as commonly as other things in this course, at least, but they do exist. And so we can have quaternary amines and amides, excuse me, as well as what's known as a carboxylate, which is what you have right here. Okay. So now let's talk about what is up with this nitrogen, because it is doing weird things. Okay. So amines are not all alike when it comes to this intermolecular force stuff. Okay. We can have a primary amine, and a primary amine looks like a structure like this. So you have some type of R group that's over here. You have a nitrogen, and you have two hydrogens attached to that nitrogen, at least two. You could also have like three would be really ammonia, but we sort of don't call that or classify that as anything. But the nitrogen's attached to a carbon chain. It's also attached to two hydrogen. What this means is it can hydrogen bond. It's happy. A secondary amine is attached to two different carbon chains. So we have one going on here, and then this guy is another one. It's still got an attachment to a hydrogen there, therefore it can also hydrogen bond. However, when we get to a tertiary amine, the nitrogen is now attached to three separate carbon chains. Doesn't matter what they are. It's not attached to hydrogen. And if it's not attached to hydrogen, it cannot hydrogen bond. Okay? So one of the things that I haven't talked about is that in order to have that hydrogen bond, when we have oxygen or when we have nitrogen, oxygen has two lone pairs and nitrogen has one lone pair. That lone pair has to be available in order for hydrogen bonding to take place. The halogens, fluorine, has lots of these guys. And then usually it's connected to something. Well, when you get to what's known as a quaternary amine, So right here. This guy would have a nitrogen attached to 4 carbons, and it takes on a positive charge on that nitrogen right there. Now, the problem with this, it can't hydrogen bond anymore because it doesn't have a lone pair of electrons. But the flip side of that coin, it's got a positive charge to it, so it doesn't actually need or get classified with a hydrogen bond anyway, because now it's an ionic compound. So quaternary amines and amides both are going to just be, ionic. And you could also have a quaternary, what's called ammonium salt, which looks like this. So basically the 4th thing that this nitrogen's connected to is that hydrogen. Again, you don't have lone pair of electrons available to hydrogen bond, so it won't. Okay. So in conclusion, primary and secondary amines can hydrogen bond. Tertiary amines have dipole-dipole interactions, and quaternary amines, or ammonium salts, are ions. Really different behaviors, really cool depending on what you have there. Now, you do have to keep in mind, when it comes to amides, you can have a little bit different behaviors similar to this. Finally, when it comes to carboxylic acids, we can actually give away a hydrogen. So this is what a carboxylic acid looks like. We've got 1 carbon attached to 2 different oxygens and a hydrogen. And when a strong base comes along, these electrons say, hey, I want to go take that hydrogen that's off there. Now, if you don't understand these little arrows, don't worry about it. But basically, what this OH and this H together make is water. And it leaves behind a negative charge right here, okay? And that's what's known as a carboxylate. And that carboxylate has a negative charge, therefore it's an ion. And that's how we look at intermolecular forces. Next, we're going to look at how this affects other things like melting point, boiling point, solubility, and in more detail. See you there.